Okay.
Okay.
Good afternoon. I'm very glad to introduce Hrvoje Tkalcic. He is head of geophysics at the Research School of Earth Science of the Australian National University in Canberra. Hrvoje got his PhD in Berkeley, and then he does lots of interesting things in the field of global seismology, also managing an array contributing to CTBTO project in Northern Australia. And today, he will show us how to look inside the Earth and possibly other planets with the coda-correlation seismic waves. So please, Roy.
Okay. Thank you, Carlo. So how do we switch again to the...
Click on the back, yes. On the back on the, yeah.
Okay, so we put in the
Full screen.
full screen mode. And Carlo, this is, I see, use a slideshow. And point. This should work now. Okay. So thank you very much for the audience here and everyone online. I'm very grateful to Carlo Giunchi for hosting my visit here in Pisa, and also Angela Stallone in Bologna, where I'll go this evening. Today I'd like to share some exciting new research, relatively new research in global seismology with you. Before I start, I'd like to acknowledge contributions from my research group. So these are, as you can see here, my PhD students and postdocs who contributed to this work. And I also like to acknowledge the support from OSCOP, which is an Australian equivalent of EarthScope and maybe Alpere or Adria Array that we have in Europe. And National Computational Infrastructure, the computational facility in Australia, as well as ARC. And ARC is the Australian Research Council, equivalent to European Research Council. And before I start, I'd like to briefly introduce where I'm from. So obviously I come from the land down under, and Canberra is the capital city, which because Sydney and Melbourne couldn't decide who is going to be a capital city. So there was some competition there. So Canberra is in between. You see, if you draw a line from Sydney to Melbourne, Canberra is 3 hours drive to Sydney and about 6 to 7 hours drive to Melbourne. 800 meters elevation in the mountains, pretty much. And this is the Research School of Earth Sciences. We have been restructured recently to 3 departments or 3 areas: geophysics, geochemistry, and ocean and climate geoscience. Currently in geophysics, we have 6 continuing faculty members, and then we have a few emeriti and about 15 early career researchers and about 25 PhD students. So altogether, about 60 people work in geophysics area in different aspects of geophysics, but mostly seismology and geodynamics. And a little bit advertisement for the Australian National University, which is a leading research university in Australia. So we have pretty much international community, PhD students coming from around the world to Australia. And these are some of international partners. It would be nice to see maybe an Italian partner as well here among these universities. But this is my research group over the years and how it's changed. from early 2010s to 2020. You can see a quite international group. This is how we look today or in the last couple of years. And these are our research interests, which pretty much align with my research interests from the time I was a PhD student, where I started working on the deep earth at UC Berkeley on the inner core seismology and seismic sources. But when we moved to Australia, then of course, due to the geographical location of Australia and vicinity to Antarctica and the Southern Ocean, you start some work in this area of seismology as well. And in particular, I feel responsibility for not just maintaining the existing infrastructure, but also expanding our observational infrastructure to the remote areas of Australia. And I will show you some slides from the interior of Australia as well as the ocean, basically ocean-going voyages to extend this research of the Australian, basically continent to the entire Australian plate. And I will show you how this contributes to our effort in global seismology, not just to understand the Australian continent. So I divided my talk in three parts. The first part is about what motivates us to expand our research to the coda-correlation. In the second part, I will introduce coda-correlation, wavefield, to those of you who might not be familiar with this topic. And then finally, I will show you some exciting applications of this coda-correlation. So my goal is to demonstrate that apart from the proliferation of seismic instruments in the years to come, these new methods such as coda-correlation is really one of the ways forward that I think will basically define global seismology, but also planetary seismology in the decades to come. Okay, so I don't think I have to spend too much time here in this institute explaining how we use body waves to probe the Earth center. And you can see here some of the PKP waves. So these are compressional waves that I use to study the deep Earth, and some of the reflections from the different boundaries, the inner core boundary here, and the core mantle boundary, as well as the reflections from the other side of the Earth. So of course, this is in a high frequency approximation, but these are the seismic phases that are used in seismology of the deep Earth. And I think it's appropriate to show this seismogram here to you. This is the 100th anniversary, pretty much, of the first observatory in the Western Hemisphere, which was UC Berkeley. And I just had a conversation with Carlo how seismology in those days was used with astronomy. So this was the first observatory or the first seismometer in the Western Hemisphere. And you can see a classical regional seismogram here with P waves and S waves and surface waves. And in global seismology, we also use these exotic phases. You can see here, this is the outer liquid core and just a sketch of the inner core. And you can see these multiple reverberations from the ceiling of the outer core. So these are the so-called whispering gallery of waves. And especially in the Cold War era, there were observations from Novaya Zemlya in Russia to California here. And you can see some examples of P4KP and P7KP, these multiply reverberating waves from the ceiling of the core. Then we, of course, pick these arrivals, and then on the horizontal axis is the time, on the is the epicentral distance or the angular distance, and on the vertical axis is the time. And if we do it many times, let's say tens of thousands of times or millions of times, we can get this beautiful representation of travel time sections where each seismic phase is colored with a different color. And then, of course, in geophysical inference, we go from these observations to the models of the Earth. And here's an example of a one-dimensional model of the Earth. And as you know, we can have the entire course on how we go from the observations to the Earth structure on the right. But if we did everything correctly, then when we compute the forward model, or from this theoretical model, we get the predictions, the travel times that pretty much match the observations. So you can compare these two. And if they match, of course, that means we did something well with our geophysical inference. Okay, but when it comes to the deep Earth, we use the geophysical inference to infer the properties of the, in this case, inner core. So here I chose an inner core as a black box. So you have some model that you can use to calculate either the travel times or anisotropy properties for the inner core, or any other property that you're interested in. And you can compare these model predictions with observations. So if they match, we are happy, we accept the model. If they don't match, we go through another, so we go through inverse problem, basically, which is an inductive process. And then we redefine our, we fine-tune our predictions until we are happy with the observations. And this is how geophysical inference works in many applications, not just seismology. But I here want to show you one example of how this can lead to non-uniqueness. And here what you're seeing is the models of the inner core anisotropy. The property that was, in this particular case, observed in 1980s, that the waves that travel along the Earth's rotation axis travel faster than those in the equatorial planes. So this was interpreted as anisotropy in the inner core, due to maybe the growth of iron crystals that can be anisotropic, and they can control the speed of compressional waves through the inner core up to 5-6 seconds or so. And you can see the results from many different papers, different models that explain pretty much the same data set. And this is a good example where you can see that you can have many models, but only some of them are useful. Or these models explain a portion of the data, but they're not necessarily required by the data. So we have to deal with this. We have to be extremely careful when we study the deep Earth, and this is something to keep in mind, right? This model non-uniqueness. So how do we address this problem? I think it's becoming increasingly clear that we have to collaborate with each other in geophysics community, and particularly with geodynamics and mineral physics when it comes to the deep Earth. But all these other disciplines come to mind, particularly computer sciences and mathematical geophysics that are insightful when it comes to the deep Earth. So all-embracing approach is required. And okay, so in Australia, we did our part to contribute to the observational infrastructure, to build more instruments to go to the remote areas. And here are some examples from our field experiments. You can see the color that dominates these photographs is red. And that's because the almost entire Australian continent is oxidized iron. You can see that it looks more similar to Mars than the surface of the Earth in many ways. And the RCS has been very active in these academic deployments across the continent. And you can see some here in the south eastern part of Australia. In particular, we have a very good coverage on the order of 30 to 40 kilometers between the stations. Our installations are fairly simple. We go to the field and we dig the sensor and protect the equipment from wild animals. And you can see some more images here from various experiments in the interior. Particularly my colleagues, Nick Rawlinson, who is now at the University of Cambridge, and Anya Redding at the University of Tasmania, were active in the early days of these deployments. And now Geoscience Australia, which is equivalent to INGV, is taking over some of these deployments at least, and with the plan to cover the entire continent. And this is more specifically what my research group and I did in the last decade. So we installed these interesting spiral arm arrays. So these are spirals. You can see here Varamanga, which is a monitoring facility in the Northern Territory. It's L-shaped, but on top of that, we installed these spiral arms, three logarithmic spirals, basically. And if you you can see here another location, but basically, if you look at these array response functions, you will see how the spiral arrays suppress the side lobes that linear arrays have, and have some really good features. So with relatively less elements, you achieve much better control over back azimuth and slowness. So we installed several of these spiral arm arrays in the Australian continent. And just recently, several years ago, we went to the voyage to the place called Macquarie Ridge Complex. And some of you will know that Macquarie Ridge Complex is the place with some of the largest underwater strike-slip earthquakes in the world. In fact, the largest 20th century strike-slip event happened here. And we don't understand these events well. They could give us some information about the possible incipient subduction in this place. So you can see this is the configuration of our proposed arrays with the spiral in the south and the more classical one in the north. So this is Australian plate, and this is the Pacific plate. And so we went to this really extreme geophysical expedition and endured the conditions in the furious 50s, where we all got seasick and had to spend pretty much the whole month there with the constant waves between 5 and 10 meters. And we managed to install 27 of these OBS instruments. And interestingly, the first result was not about earthquakes. It was this sonar image really shows you how steep the bathymetry is in that part of the world. It's actually the steepest bathymetry on the planet. From the base to the top, it's 6 kilometers, and this little island, Macquarie Ridge, is about 35 kilometers long. And the first thing we discovered is that there's an evidence, really clear evidence for these really the huge mass wasting events on both flanks. So this is the view from the south to the north. And you can see here on the eastern flank evidence for these large landslides that were possibly responsible for large for large tsunamis in the past. So this is an example how we went to study earthquakes in this part of the world, but basically found evidence for some tsunamis, which we are now trying to understand along with the seismicity here. Basically, we observed more than 1,000 earthquakes in this less than 1 year from the data that we got. And this is currently what we are doing. So the bottom line here is that with the increasing of observational infrastructure, I will show you an example of a very recent observation where we were able to capitalize on the large number of seismic stations that were deployed in the field. So here, for example, in Alaska, you can see by blue a large number of stations, and you can see an event in Alaska. And for the first time in the history of modern seismology, we observed these multiple reverberations through the Earth center up to 5 times. And this ended up on the front pages of the leading newspapers, which is very good for global seismology that there was such an interest in this. But let me show you some real observations here. Here is a Solomon Island event, and on the opposite side of the Earth, so basically antipodally, we have many stations. And here is a sketch of these ray paths through the Earth center, and you can see on the clear, on the travel time sections here on the right that we observed, of course, PKIKP, then PKIKP2, it's 1 reverberations, and then 3, 4, and 5, very clear arrivals based on a single event. So this is based on a single event and on the order of more than 1,000 stations. When you stack them together, you see these beautiful multiple arrivals that we call ricochet waves through the Earth center. And here are some more examples from different events. And you can see some clear evidence for example, PKIKP4. So the compressional waves that travel through the Earth center basically 4 times. Okay, so here is an example of how this coverage of the inner core looks in 3D. And so the green dots here are stations, and the red dots are large earthquakes, and the gray ball in the center is the inner core, and you can see it enlarged here on the right. And you can see how in the high frequency approximation, with the existing configuration of sources and receivers, what type of coverage do we achieve of the inner core? So you can see in the north, we have a pretty good coverage, but in the south, we have a large gaps, especially in the Southern Ocean and in the Southern Hemisphere in particular. So while on the 2D maps, the coverage of the inner core might look good, when you look closer using a 3D animation like this, you can see that we're still very far from the coverage that we would like to achieve to be able to do tomography, for example, of the inner core. And this really brings me to the second part of my talk. What is a coda-correlation wavefield and why we need it to advance global seismology? So I'd like to give a really simple definition of coda correlation. So as in music, you know that the coda is the last part of the composition where things get resolved. In our studies, we are going to now do quite the opposite, right? So we are going to, instead of first 3 hours, which is here showed in a black, we are going to throw it away. So the first 3 hours of the record with the major arrivals, P waves and S waves and surface waves and so on, we're throwing that away. And we are going to focus on the red part, everything between 3 and 10 hours after the origin time. And as you know, the cross-correlation is defined this way, where you basically compare 2 time series and you're measuring similarity between these 2 time series. And then you can express that similarity between 0 and 1. And here's an example of a very simple waveform. Of course, the seismograms are much more complicated, but it's the same idea. And the third thing that I want to mention is a global correlogram, which here is shown here at the bottom. I'm going to demystify this plot in a second. It's a beautiful 2-dimensional plot that looks very much like the travel time sections. But I will show you some studies that when we started working on this back in 2017, 2018, this was state of the art. So you can see here on the left, the classical travel time section, which I already explained. And then you can see here on the right, the work of my colleague, Pierre Bouet from Grenoble. So during the seismically quiet days, this is what you obtain when you compose the global correlogram, something that looks very similar to the seismic stacks. And the days with earthquakes, you obtain this global correlogram, which has some similar features, but it also has these very almost zero slowness arrivals that are here characterized by these horizontal lines at the edges. And what you also see are these spurious phases. They were called spurious in the community because there was no adequate explanation for why these should exist at the first place, because they occurred before P-wave arrivals. They shouldn't be there. If everything that we see in these correlograms is due to the constructed body wave arrivals, like what the community that does the ambient noise is seeing, then there's no explanation for spurious phases that arrive before P waves. But I'll get back to this. I just want to tell you that everything we do, we benchmark with numerical simulations, and here we use AXIS-M. So here's an example of the observed record 10 hours after the origin time, and here's computed by AXIS-M for the same amount of time. So the first thing I want to show you is how this global correlogram is constructed. And I want to demystify this a little bit. I chose 2 stations in Australia. They are 15 degrees apart. And so 15 angular degrees apart. And Australia is surrounded by seismicity like this. So these are all large events, larger than magnitude 6.8. So you take any one of these events and you cross-correlate the record on these 2 stations from that event. And this is what you obtain. So this is the cross-correlation function, which is filtered between 15 and 50 seconds. So you can see some features here where obviously these two seismograms were similar. So they resulted in a peak in the cross-correlation function. Now, in the next step, we can repeat this, but now for every single station pair between 15 and 16 degrees that we can identify on this map. So you can see many station pairs in this particular distance bin between 15 and 16 degrees, and all of them are stacked here. So again, cross-correlation computed, all stacked here, and you can see many more features now for such a stack. Then we take this and paint the positive amplitudes in blue and negative in red. And then we show it as this strip here between 15 and 16 degrees in blue and red. Of course, you already guessed the next step, and this is now to identify all possible combinations of station pairs in every single distance bin to populate this 2D global correlogram. And when you do that, when you find all possible combinations and then repeat the exercise, stack them together, filter between 15 and 50 seconds, you obtain global correlogram, which is here shown on the right. I like to call it the fingerprint of the Earth, because basically you will see in the rest of my talk what we can learn from this global correlogram now, which is based completely on the similarity. So it's you have to switch your brain from thinking about travel time sections to a mathematical wavefield, where every single feature that you see in this correlogram is due to the similarity of the waveforms. Okay, so, and I'm going to focus on this particular negative slowness feature here in the lower section of the correlogram, which there was no adequate explanation of what this is, right? If all these features are actually in some way reconstructed body waves that people in ambient noise community observe as well, then there's no adequate explanation for this. And in fact, here's the zoom section. So it's the first 20 minutes of the correlogram. So it's a lower left corner of what I just showed you. And you can see some arrivals or some features here that are pretty much similar to P waves or PCP waves or SES and so on. But you can also see these in these yellow windows, the very strong features that are not adequately explained. And I'm going to focus on one of them that's called CSCP. It's here in the lower left corner. And I will show you how we explained it. Basically, with a very simple principles, like basically back to the school first principles of physics, how we actually explain these arrivals in the correlograms. So you can imagine here the core mental boundary as the largest or the most extreme boundary within the Earth, where the density contrast exceeds the density contrast at the Earth's surface. So it is really feasible to think that the core mental boundary is going to present the major boundaries where energy partitions from P waves to S waves and so on, and contributes to some of these observations. So imagine the P wave field deriving from the core and hitting the core mental boundary from below. And you have two receivers on the Earth's surface, R1 and R2. We all know that there is energy partitioning from P to S. So part of energy will continue as P waves, but part of it will continue as S waves. And so the P waves are going to be observed on R2, S waves on R1. When you compute the cross correlation, you're going to obtain this peak here. This is due to the similarity of P and S waves. Now, we also know that each point at the core mental boundary acts as a Huygens, as a new source of energy. So basically, a new point according to the Huygens principle. And we can compute for each one of these points exactly the same cross correlations. And we show it here on the horizontal axis as an angular offset from the center here to the left and to the right. And you can see when you stack these cross-correlation functions, what survives really is the maximum, this maximum peak which corresponds to the so-called stationary points. So these are basically the minima of the travel time difference between P and S waves. Everything else destructively interferes, and only this, so basically the contributions due to these stationary points survives here, and it contributes to this peak in the cross-correlation function. So now we can repeat this for any single distance, for any choice of distances between R1 and R2. And when we do that, we obtain synthetic cross-correlation functions as a function of interstation distance here. And you can see it has a negative slowness. And this is exactly what we observe in practice. So by using these first order principles, we were able to explain the existence of the so-called spurious phases in the global parallelogram, where everything again is due to the similarity of the reverberating waves. I can show you this in a slightly different, from a slightly different point of view of the ray theory. So you can see again R1 and R2 here. And if you have a source such that the reflection point at the core mental boundary produces P waves and S waves that are observed at R1 and R2 with the same slowness, they are going to contribute to the maximum of this cross-correlation function. And not only that, but any source anywhere else on the Earth with basically these two legs in common, but with all these other legs that are different, they only contribute to these two arrivals with the same slowness. They will also contribute to the peak in the cross-correlation function. So basically, everything that is similar, which arrives at the same slowness to R1 and R2, is going to give rise to this correlation feature that we observed in the global parallelogram. At that point, we realized that it's not only these spurious phases, but pretty much everything we observe in the global parallelogram, such as, for example, PKP, and that's why we call it PKP star, because it's really not the physical PKP waves. So here you imagine R1 and R2, and if you have a source in this point, you're going to observe PCP waves at R1, and you're going to observe PCP and then PKP at R2. So that's a phase that bounces off the Earth's surface and travels to R2. So when you compute the travel time difference between the two, you're going to get something that is equivalent to PKP waves. So again, PCP, PKP minus PCP is going to be equal to PKP in terms of the travel times. So when you see PKP, something that looks like PKP in the regular direct wave field, it's actually not the PKP. It's there due to the similarity of all these other reverberating phases that give rise to the peak in the cross-correlation function. Okay, So this is the point where we realize that the coda-correlation wavefield, if we can explain every single of these features, could be used as a new paradigm in global seismology. Because these reverberating phases, many hours after the origin time of large earthquakes, have a very different propagations through the Earth. So their sensitivity kernels, if you want, are going to be very different from the direct seismic wavefield. And I'm going to show you, but before I show you some application, I just want to tell you this story. And this is our observation of particular seismic sources with particular focal mechanisms that contribute to the clarity of the global correlation, global correlograms. Here's our search through the catalog of really large events. And what we found is that only those with particular focal mechanisms, that is either reverse or normal, and with a very simple source time function, can actually produce correlogram that is equal in quality to the one that I showed you before. So here we now don't take 200 or 300 events. We take a single event. So single event and stations around the globe, we produce the global correlogram in the same way from a single event. This is good news because if you want to perform numerical simulations, you only need to do it for a single event, right? And produce 10 hours after the origin time to compare it with the observations. Okay, so in this part, I would like to briefly show you some exciting applications of this and what this means in practice for global seismology. And we have done since 2017 and 18 many studies. And today, of course, I don't have the time to talk about all of them, but I will focus on some current and future studies with maybe only one or two observations that I think are really outstanding that I would like to feature, particularly this one. This is about the inner core and about the solidity of the inner core. So some of you know that when Inge Lehmann discovered the inner core back in 1936, in 1940, the Francis Birch, an American mineral physicist, proposed that what Inge Lehmann had observed in 1936 is actually a transition from solid to liquid iron. And since then, there was a search for the so-called PK-JKP waves. So J here stands for shear waves in the inner core. So this would be PK, basically compressional waves that convert to shear waves at the inner core boundary, travel as shear waves to the inner core, and then they're observed as a PK-JKP as opposed to PK-IKP. The only problem is that these observations were really elusive. So the community was quite divided on the quality of these observations. For example, you would see for one event only one observation on one station, but you wouldn't see it on other stations, and so on. And for many events, there would be nothing where we predict PK-JKP. And therefore, this funny cartoon here, because this was considered as the holy grail of modern global seismology that would actually confirm the solidity of the inner core. There were other observations, particularly from normal modes community, that showed that the inner core was solid back in early 70s. But these PK-JKP observations in particular were very rare. And as I said, community was divided. So what we decided to do with a global correlation wavefield is to check if we can devise a scheme to show that we can use global correlation as a new method. And here, the idea was to basically change the shear wave structure in the inner core. So it's almost like fine-tuning the inner core shear wave properties. And I will show you what happens when you change the shear wave perturbations from minus 15 to 20% with respect to preliminary reference Earth model. And because the inner core is small, basically less than 1% of the volume of the Earth, you would expect that when you change something in the inner core, it wouldn't affect the global correlation wavefield that we see here. And if we can see the change, that means we have a method that's actually sensitive to the changes in the shear wave speed. And here is what happens when you change shear wave speed from minus 15% to plus 20%. You can see that the global correlation wave field is pretty much stable, and this is what we would expect. Except in this window B here, you can see the cusp of energy that sort of goes up and down, right, as we change the shear wave speed. So to make a long story short, we identify this cusp of energy here due to the similarity of PKIKP, PKIKP, and PKJKP waves, right? So you have, if this is your source, then you will have PKIKP, PKIKP on one receiver and PKJKP on the other. So when you measure the similarity of the waveforms, you actually get a pretty pronounced cusp of energy here in these very short angular distances or interstation distances. And when we compared that with the observed correlation wave field, we were able to compute that the shear wave speed in the inner core is 2.5% slower than predicted by PREM. To some, this is not a surprise because PREM is basically constrained with the long period waves with the normal modes. And it doesn't have that much sensitivity to the inner core, particularly when you go towards the center. Whereas correlation wave field is highly sensitive, as you can see here, to the shear wave speed variation in the inner core. And most recently, we redefined this research. We refined it with some more clever data pre-processing and data processing methods. In particular, as I already mentioned, if you select only reverse and normal mechanisms, you will increase the clarity of these global correlograms. And this is to be expected because for normal and reverse mechanisms, you can see that the P-wave energy is going steeply down and is going to contribute to these reverberations many hours after the origin time. Whereas for strike-slip events, this is not the case. And the second thing that that matters is really how you select the source and the receiver pairs. It turns out that they all have to be on the same great circle plane to be able to constructively contribute. And when we did that, we obtained that the shear wave speed is even a bit more reduced with respect to PREM. So we get 3.5% reduction. Okay, so with this method, we then, the next thing on to-do list really was to construct a new model of the Earth. So new 1D model of the Earth, but now in this period range between 15 and 50 seconds. And this is exactly between PREM, which is constructed using normal modes and the long period waves, and for example, AK-135 or YASPE, which are constructed by using a high frequency, about 1 Hertz waves. And we did that by waveform modeling of these correlation features. And for that, we used 71 correlation features in the correlograms that we could identify. And here's some comparison with the observations. And you can see here on the left is a PREM, and then AK-135 and EK-137, which is a new AK-135. And then the last column is a CCRM. And this particular feature is called PCP star. And this one is K4 star. So that's a 4 reverberations in the outer core. And it's equivalent in the correlation wave field. And you can see how CCRM performs in comparison with these other models. And now something really interesting, and that actually has to do with the outer core. In this exercise, we divided our stations with respect to the latitude to the polar and equatorial group of stations or receivers. So when you do that, basically, you can compute the global correlograms in exactly the same way. And you can see that the global correlograms that we obtain from the polar and equatorial group are pretty much the same. There's no way to tell the difference between them when you look at these two correlograms. And indeed, when you compare the waveforms, so when you compare some features that are sensitive only to the Earth's mantle, you don't see any difference between polar and equatorial group, as you can see here. One is in black, one is in gray. However, when you look at the liquid outer core and the features that are sensitive just to the outer core, you can see a huge difference between the polar and the equatorial group. The polar group being advanced by about 6 seconds in comparison with the equatorial group. And again, to make a long story short, we tried to model this by the tangent cylinder. This is a Taylor cylinder that exists in the liquid outer core due to the presence of the solid inner core. And you can see here another model which has a low velocity at the bottom of the core and at the ceiling of the core. This is what contemporary observations suggest. And you can see that in both cases, you don't obtain the observed difference between polar and the equatorial group. Only when you have a structure that looks like this, which is in mathematics, this is called torus. So when you have a torus shape or equatorial sort of belt in the liquid outer core with the low velocity zone, you can explain this first order observation in a global coda-correlation. We don't know what it is yet, but I would say this is a first order seismological observation, which is equivalent to our observations of the first order discontinuities, for example, or when the inner core anisotropy was first proposed back in 1986. This is exactly the same order of how many seconds you get in terms of the difference between polar and equatorial paths. Okay, and so what we are doing at the moment is we're trying to construct the sensitivity kernels of the coda-correlation wavefield itself to be able to perform mental tomography. And in this particular case, we are going to focus on this P star feature that some earthquakes really produce a nice P star, which again is due to the similarity of the waves that reverberate through the mantle, such as PPP minus PP would give you something that's equivalent to the P star, right? So you have a very complex kernels, and this animation here, if I can run it, it looks like I can't, would show you the propagation of the coda-correlation wavefield, but hopefully I can show you here how the sensitivity kernels look for this particular window. So again, these are some of the features that we observe very strongly in the coda-correlation. And when you use the adjoint method, this is what you obtain, right? So first you have to make a long story short, you need to compute the direct wavefield, and then you need to compute the adjoint wavefield. When you put them together, you can start obtaining these kernels that really show how the shear wave and the compressional wave and the density change when you perturb the Earth structure. So hopefully you saw in some of these kernels some of the features that look very much like long paths that bounce off the Earth's surface and travel through the center. So you can see how complex these kernels are. But now that we computed them, we can use them in the same way that they're used in global tomography with the direct seismic wavefield to obtain tomography models of the Earth. Okay, and so this brings us also to some planetary exploration and how we can use global correlation to study the structures of other planets. And you might ask yourself, how on earth would you do that? Because on Earth, we have thousands of receivers and we have large earthquakes. On Mars, so far, we have observed only about 20 events that are long, that look pretty much like earthquakes, right? In terms of their frequency content, and so on. But we only have one receiver. So in this study, we again use the mathematical trickery, the reciprocity theorem, to replace the locations of receivers and sources. So our InSight seismometer becomes a virtual source. So it becomes a virtual Marsquake. And all observed Marsquakes become virtual receivers. So when you do that, it turns out that you can compute the correlation wavefield in the same way that we do on Earth, right? So now we are also helped here by the meteorite impacts, because for meteorite impacts on Mars, you actually have orbital images. So you know exactly the location. So you can use them as a ground truth event. And when you do that, and when you look at this particular feature that I explained, CS minus CP, where C here stands for the core, right? And then S waves and P waves, and the similarity of core basically originated S and P waves. You can compare the observations with predictions, and we were able to measure the radius of the Mars core based on this new method. Okay, so how much have we done, and what will the future look like? I like to think that we have pretty much explored the Earth with the seismic wavefield, even though we are still in the discovery stage when it comes to the deep Earth. But we have also explored Mars with more than 300 papers published just from a single seismometer on Mars. But when it comes to the correlation wavefield, we have really just started using it on the Earth and really scratched the surface of Mars. And finally, when it comes to the Moon, this is really exciting. I have a slide here that shows you some of the unanswered questions and objectives when it comes to the lunar interior. And I'm really proud to say that Australia is going to be one of the countries that will land on the Moon. So the landing is planned for 2026. With other countries, we hope to get some good broadband waveforms where we can apply the same method, the coda-correlation method that I introduced here, to study the lunar core, for example. The same for Mars. Even though there were 300 plus peer-reviewed papers published, there are still many, many unanswered questions, including these first-order questions on the, for example, origin of Mars dichotomy, or why the magnetic field ceased on Mars, and the core structure itself. Okay, so with this, I hope I demonstrated to you that the coda-correlation wavefield is a mathematical wavefield that we can use as a complement to the direct seismic wavefield. I also hope that I illustrated that the features that we observed in the global correlograms are all there due to the mathematical similarity, right, of the waveforms. In particular, these late reverberating waves through the interior. So they are definitely not reconstructed body waves, as we see on the Earth's surface, where we have a diffuse wavefield. Here, this particular, the seismic wavefield through the Earth is not diffuse to the point that we can reconstruct these arrivals. So I hope I demonstrated that everything we see, and you could see that from a single event, that is really due to single event reverberating waves. And I showed you some applications, and I just want to say again that the similarity between two weak signals becomes a really powerful tool. So that becomes even more prominent than the weak signals themselves. And that's really what we capitalize on in these studies. And I just want to leave you with one last thought, that while we are in the mapping stage when it comes to the Earth's surface, we are still in the discovery stage when it comes to the deep Earth, and looking at the core of the Earth and so on. And that's what makes this field really exciting and fascinating. I think it will continue to fascinate us in the next few decades. So thank you very much for your attention. Exactly 4.
So thank you very much, Hrvoje, and we will be very happy to take some questions, maybe from remote, as we have one. Could you please help me?
Yes, there is the president, Carlo Doioni.
Yeah.
Thank you so much. It was a great talk. Very impressive.
Thank you.
And thank you. It was very stimulating. As INGV, we are starting with a project trying to look to have a telescope into the Earth. So it would be great if you could cooperate with us. And with this coda information is really powerful. I would have several questions, but I'm asking you whether you know you worked on you can resolve the relative motion between the inner and the outer core in terms of relative speed.
Okay, so thank you very much for your comments. And I just today, in my discussions with Carlo, I commented that this phrase of the earth science and seismology being used as an inverted telescope is widely used, and I really hope it can continue to be used. And I think we should learn from our colleagues astronomers who get great amount of funding and support from the community. So hopefully we can achieve something similar, although on the smaller scale. And to answer your question, if I understood correctly, you asked me about the differential rotation of the solid inner core with respect to the mantle of the Earth. Is that correct?
With respect to the outer core?
Yeah. So this geodynamics community likes to use the Earth's mantle as a reference frame.
Okay.
But yes, we have of course done some work on that, which I didn't present today. I think the community is getting to maybe converging to the idea that what we can observe seismologically is a fluctuating rotation or fluctuating differential rotation with several decades. So what that means is the positive rotation or super rotation for a few decades, and then negative or reverse rotation with respect to the reference frame for a few decades. And I think there are many studies now, particularly in the last couple of years, that demonstrated that it's feasible to observe that seismologically. Although it's fair to say or to make a comment that this is still debatable, and some people think that what we observe seismologically could be due to the dynamic topography at the inner core boundary, rather than the rotation that we can actually determine seismologically. But as you know, this idea comes from the geodynamo community, and on the intuitive level, it's easy to think about the differential rotation of the inner core due to the constant balance between the gravitational and electromagnetic torque.
Thank you.
You're welcome.
Do we have other questions? And
if there is no other question, I take advantage to one more. And you didn't talk about the growth of the inner core. I mean, we know since Runcorn that the inner core didn't exist before 2.5 billion years ago.
Yes.
So
Yes.
it's the cooling, and also very much interesting is your new model about like Prem or Rapkin 135. I mean, the application for seismic tomography would be very interesting.
Yes, no, thank you. Today Carlo asked me to talk about the coda-correlation, so I actually didn't focus on the inner core itself. I'm giving a talk in Bologna on the inner core, but you're right. So the one of the largest uncertainty in not just in our science, but I think in the science in general, is some of the parameters that are associated with the inner core. And one of them is the age of the inner core, and at which point in the Earth's history the inner core starts solidifying and growing out of the liquid outer core. And I think the range these days is anything between 200 to 300 million to more than 2 billion years. So that's how big this uncertainty is. And some papers suggesting that the growth rate on the order of 1 millimeter per year. So
Yeah.
if you compute back, that would give you about 1 billion years. But how exactly it changes over time, I think I didn't have a chance to mention the innermost inner core. And I think that's another really interesting topic that's developing, and many studies that are now converging to suggest that there is an innermost inner core. And the innermost inner core, that transition between the innermost inner core and the rest of the inner core is much more subtle than the first order discontinuity. It's actually a change in the anisotropic properties. And so if you want the innermost inner core, the slowest direction of propagation is in oblique angles with the rotation axis, whereas in the rest of the inner core, the slowest direction is in the equatorial plane. So what exactly caused that? Maybe some catastrophic event in the Earth's history, and why the iron crystals would start growing in the different directions. It's still a mystery and still a subject of studies. So hopefully we are, I think there are many uncertainties, but we have also made a lot of progress. And when my book was published back in 2017, it was maybe this thick, but now it will probably be 2 times thicker because of the progress we have made in the last 5 or 6 years.
Thank you.
Okay, thank you. There are other questions? If not, I may have a question for you.
Sure.
And I think that your works is brilliant because show that the effort to deploy broadband station all around the world is well deserved to get such results. And my question is about the limiting factors of this kind of research. What is the hardest part currently? I mean, the lack of observations or computational power, which is the...
Well, I would say a combination of both. There's still a lot of space for improving in terms of the computational power to push to the 1 hertz. And if you ask anyone from the computational community, they will say that this is really, that's where the demon is, the 1 hertz.
1 hertz.
And that's what we're trying to reach. But I would say that, the most limiting factor for global seismology is uneven coverage. You can compare that with the tomographer, medical tomographer, who's trying to figure out, the cancer in the human body where only one side of the sources is working. And in our case, the largest earthquakes are in the subduction zones that are all confined within the equator, with only few exceptions towards the pole. So that really limits, it's not realistic to expect that we are going to get large events towards the polar regions in the years to come. So that won't change. So from that point of view, coda-correlation is really a revolutionary concept, because all of a sudden you have a control over many different propagations, that we don't have with the direct seismic wavefield. So hopefully we can capitalize that. It's still a developing field, but these first few applications, I hope, show the potential of the method.
Thank you. And okay, I think if there are no other questions, thank you very much again. Thank you.
Thank you all again.
Okay, I can stop the record.
Yes.
Thank
And for those of you that are interested, I think that there is another seminar by Hrvoje Friday that and will be also streamed by remote. So
Slightly
provide,
changed,
yeah.
yes. Maybe a bit more focus on the inner core.
okay. Thank you.
Thank you,
Thank you so
grazie again.